This part, Lecture 8, Part 2, we will study microarchitecture for R-type instruction. Before going to the R-type instruction, keep in mind that you guys already know the microarchitecture for load word and store word instruction. If you don't know the instruction, please have a look on this previous video and then start studying this one. This is a quick review of the behavior of store word and load word microarchitecture. So in store word, perhaps in load word as well, the ALU always receives the source B operand from the sign extended immediate. So this is fixed, that the source B comes from the sign extended immediate, because in both the load word and store word instruction, this ALU used to calculate the memory address that having a base address from source A and the offset from source B to get the memory address where you write or from where you read. This is one thing you need to keep in mind. Another thing is, in load word instruction, the register file always got its write data from the data memory. So here, whatever in the data memory, the load word comes here and write directly through this port. Also in load word instruction, the register to write was specified by the RT field with the instruction 16 to 20 here. So this is the common thing that use store word and load word. Again, a quick review. The source B of ALU always comes from the immediate. The register data file always comes to the read data from here in the load word instruction, and the instruction come here with the A3 port to write the data from the register. These are the common behavior and microarchitecture of the load and store word instruction. Now let's move to R-type instruction. We all studied R-type instruction while we are studying MIPS assembly language. So, for example, addition, subtraction, logical AND, or SLT, these are the R-type instruction. The common phenomena is read to register from the register file, perform a arithmetic logic unit operation on them, and write the result back to the third register file, right? So the differ from the one operation to other operation is the ALU operation. So both of them are received value from the register, make some arithmetic operation, and store the result to the other. So the only difference in the ALU control signal. So all the register type instruction can be handled with the same hardware with the different ALU control signal. Quite interesting. So we will now design that hardware that can handle the R-type instruction on top of the data that we have for load word and store word instruction. So basically we will add some multiplexer in our existing data path that we have developed for load word instruction and store word instruction. And here is it. So if you carefully think about the behavior that I have told you in the beginning of this lecture, that in ALU for load word and store word instruction, it always use the source B from the sign immediate. While here we can read it in store word instruction, the ALU always receive its source B operand from the sign extended immediate here. So now what we have to do, we add a multiplexer to source B here from either from the register file RD2 port or sign immediate, because you know in the R-type instruction we need to perform the arithmetic operation between this source 1 and source 2. So we need to addition or subtraction with the address A1, A2, that means the data of RD1 or RD2. So here is the controller of ALU source. If the control is set to 0, that means the source B of the arithmetic logic unit will receive RD2. Otherwise, if it is 1, the ALU source is set to 1, it receives the sign extended value, that is for the load word or stored word instruction. The first thing we solve with a simple multiplexer. So now if the ALU source set to 0, so the ALU will receive two operand RD1 and RD2 to the ALU. And now based on the control signal of ALU, it performs the operation here. So till now one problem is solved. So we can select both sign immediate for load or store, or the source register 2 for the R type instruction. Well, now move to the second issue. In load word instruction, the register file always got it right data from the data memory. The first lecture I explained it briefly. So it always comes from here. Particularly in that stage, we will get the memory address. And this memory data is supposed to be right in the register file. But in case of arithmetic in case of R type instruction, you don't need to access in the memory. Perhaps you have to write this result to the register file. So what we did, we put this value extended here and make a memory register selector. If the selector is set to 0, it passes the ALU result here to write the register file. On the other hand, if it's set to 1, then it receives this RD value from here and it passes it for the writing position. So another issue has solved. The first issue, the ALU input, and the second issue is ALU output are solved with two extra multiplier. And in case of store word, we don't care about the value of this because store word doesn't store anything or write anything to the register. Store word store the value to the memory. So in case of store word, don't care about the value of the memory register. And finally, this is another part. So in case of load word instruction, the register file write was specified the RT field of the instruction. If you know the instruction of load word, so there is a RT field, particularly the bit sequence 20 to 16 in a 32-bit MIPS instruction, and that particular bit is read by the A3 with the port number 20 to 16 here. Is hard-coded 20 to 16. But the problem is in your register type instruction, the destination register is set to 15 to 11. That means you need to write the value of ALU result in a register that address is defined in 15 to 11 bit sequence in the instruction. So now you cannot put the A3 port fixed for the 20 to 16 because the RT and the destination RD is not same bit sequence in the instruction. Let's move to the load word instruction here. So this is the sequence where you need to write the address, but here, here. Well, so the register, we will see the example later. The register, you need to write the result is define the address of the register in bit sequence 11 to 15 in the instruction of 32-bit register. So we need another multiplier here that select either it's RT or RD. In case of RT, in load word instruction, the bit sequence is 20 to 16. And in case of RD, in the R-type instruction, the bit sequence will be the 15 to 11, where you need to write the value, or you need to write the address, you need to write the result, ALU result, right? Well, and in case of a store word instruction, we don't care about the value of this register set. And you know that there is also a control called the register destination, REZDST. If the register destination is set to 1, that means it's an R type, so you have to write the bit sequence 15, 11. Okay. So these three multiplier, one is for selecting the destination to the ALU, another is passing the result of the ALU, and the third one is writing the value to the target destination register. So these three multiplexers combinedly makes the hardware, the data path that also support for R type. Of course, the value for ALU control is different based on the instruction. It could be add, it could be subtract, it could be logical operation or anything. Well, I think if you guys have an example, it will more clarify the facts. So we have a format is, this is the opcode, register 0, register 1, register 2. The assembly is like that, add S0, S1 and S2. That means you need to add the value of S1 and S2 and store it to the S0. Whatever the value of this sequence, the register name, so this is the register 2, add the value of register 1 with the register 2 and store it to the register 0. Well, this instruction is a binary bit sequence here. So as I said, the destination sequence is 15 to 11 here. So what this in the particular case, the bit sequence 15 to 11, it says S0. That means you have to write your result of addition operation in a S0 register, because 15 to 11 is set as 0 as a destination register, and then you have to add these two registers. Okay, before going to the data path, one thing I would like to clarify to all of you. So R-type instruction read from two source register, and the bit sequence is instruction 2016 to 2125. Okay, well, and then write the value to the register, the instruction of 11-15 bits. Okay, so we have to define this bit here, source 1, source 2, and the destination. Particularly, more specifically, we need to add these two value stored here. So addition bit sequence is 16 to 20, 21 to 25, and add 11 to 15. Well, let's move to the data path. The first thing is we have two source register, 25, 21, 20, 2016, and these are comes here. the ALU source register set to 0, so it passed the RD2 to the ALU. So the ALU received the source A and source B as the value of register 1 and register 2 and register 1. And based on the control signal here, particularly add, it performed the addition operation. And again, control signal set to the memory to register is 0. That means it passed the result to find the register file. Now comes here, in the case of our register R type instruction, the destination bit sequence is 15 to 11, so it set the register destination flag or control to 1. That means it write the value by A3 with this destination register. Well, so finally now we will look example with the value in every space. So as I said you earlier, the instruction looks like here. Here is the 32-bit R-type instruction, particularly addition instruction, and that add these two register contain and store it to this register. We'll come to the data path. Before going to the data path, the given value for the program counter, say for example, is given to here 004002000, and I also give you another value for the source register S1 is 0001000 and S2 is 0001000. That means we need to add these two value and store it to the destination register S0. Well, let's have a look on the microarchitecture here from the beginning. So the program counter read that instruction and decode it to this bit sequence. First A1 will receive the bit sequence 25 to 21, that means S1, and A2 will receive the bit sequence from 16 to 15, that means S2. So A1 is received the address of S1 and A2 receive S2, and here in RD1 and RD2 we will get the value of S1, that means 0000100, and here in RD2 we will get the value is 00010. Now the ALU source flag is set to 0, that means it select RD2 to the ALU here, and also the ALU control set to the 010, that means addition operation. So source A is basically S1, this value comes here, and source B is basically this, and this value is come here, and these two are added through the arithmetic logic unit because the control set to the 0. Now, unlike the memory operation, this is not a memory address, rather this is the ALU result, so it not look for the memory, perhaps it go here and directly to the register file. Well, to do that, the memory to register flag or control is set to 0, so this selector will pass this value to here. Now what A3 receive? Okay, so as you know, according to the behavior of register file, A3, if the register address A3 is to write the value here in the particular register. Well, so here is another multiplexer that particularly select which register address go to the A3. In this case, the register destination is set to 1, that means so A3 will go the bit sequence 15 to 11. Come here, The 15 to 11 is here, that means S0 is the destination register. So as the register destination set to 1, so here the A3 will receive the bit sequence of 1511. That means the bit sequence 1511, you write a binary code which is the address of the register S0, save register 0. So it write the value of this 00001010 after addition of two cells to source register. It write the value. So the value of S0 is now changed with this value. And after that, the program counter fetch the next instruction by adding 4 to the existing program counter. This is the way that we can extend our data path until the R type instruction. In the next video, we will discuss about another microarchitecture, is branch instruction, and this is the end of this video. Thank you.